over. All right, so the difference in a linear and nonlinear function, if you have a straight line, do you see the word line, L-I-N-E, in the word linear? If your graph forms a straight line, it's considered a linear equation. If it is in a straight line, it's nonlinear, okay? And that's what our lesson is about today. So not too bad, not too bad. All right, so linear functions are graphs that have straight lines and represent a constant rate of change. So remember, we've been talking about another term for constant rate of change is slope. So if the slope is constant for the whole table or the whole graph, in other words, it doesn't change directions all of a sudden, it's a linear function, okay? So nonlinear functions, they might have parts of it that looks like a straight line, but when you look at the whole graph, you can see that this is not, all of this graph is not a straight line. And so, and also it changed direction. So here our slope at the beginning was going down and to the right, and then it changed directions and started going up and to the right. So that means the rate of change changed, or the slope changed. And that would also tell you that it is non-linear. All right, looks like Ollie's coming in now. All right, hi, Ollie. All right, so look at this one, Eli, this one right here. Is this linear or non-linear, Eli? This one over here to the left. Is this linear or non-linear? Eli, can you hear me? Okay. Do you see which one I'm circling with my mouse? Is that a straight line or not? No, it's not. Right, so it's non-linear. Non-linear. All right, Naomi, look at this one right here. Naomi, is this linear or non-linear? Naomi. Linear, this one's a straight line? Yeah, I think you were looking at the next one. Yeah, this one right here, non-linear, right? That is definitely, yep, you're right, non-linear. All right, Americus, what about this one right here? Is this graph linear or non-linear, Americus? She typed to me linear. You guys can actually talk to me, but yes, you're right. How about Ashlyn? Ashlyn, is this graph right here linear or non-linear? This one? Is this a straight line, the whole graph? This is non-linear, right? Yeah, non-linear. All right, what about this one? Camden, is this linear or non-linear? This is definitely linear, isn't it? Good, Camden. That's a straight line. And then this one right here, Kylie, is this linear or non-linear? The last one is, what's the answer? This is linear. Does everyone understand the difference, guys? If it's a straight line, it's linear, okay? If it's not a straight line, it's non-linear, okay? Everybody got it? Okay. All right, make sure you understand that. And there's the answers. Yay, we were right. We were right. Okay. Does that make sense? No, it doesn't make sense. I'm assuming it makes sense, right? Okie dokie. Now, I'm going to take the information on these graphs and I'm going to graph them, and then you're going to tell me whether this table and the graph represents a linear function. Okay, so let me get my pen going up here. So this first one is telling me basically it's a falling parachute jumper. This is the time and this is the height from the ground. Okay, so at 0 seconds, this parachuter was 300 feet from the ground, right there, okay? All right, and at 1 second, this parachuter was, let's see, is this counting by 80? Let me start at 2. 2 and 270. Right up here. Okay, and then at 3 seconds, this person was, oh, these numbers are so close together. Oh my goodness. 4 seconds and 240. All right, that's not a good graph because the numbers are so close together. Let's look at our falling bowling ball. We'll come back to the parachute jumper in just a second. 60, so these are going up by 30. So this would be 90. So this is going up by 30. This would be 270. So at 2 seconds, it would be right on this line. Oh, I'm sorry. Let me do it again. All right, so these are going up by 30, 270. This is 300. It's going to be right in the center at 1 second. 2 seconds is 270, 255. It'll be right here. And then 4 seconds. Okay, that's better. That looks a little better. All right, let's do the falling bowling ball. What about 0 seconds? 300 for 0 seconds. 1 second is 284. So 284 would be, this is 270. This would be right up here. 2 seconds, 236 would be about right here. 3 seconds is at 150. So 3 seconds would be right here. And then 4 seconds will be down here. All right, so if we connected these dots right here, can you guys see this is going to be linear? You guys know I struggle with drawing straight lines, right? But look at these. What if I connected these dots? Is this going to be a straight line? I mean, obviously I can't draw a straight line, but no, this is nonlinear, right? This is nonlinear and this one's linear. So the parachuter would draw at a consistent rate, but a falling bowling ball for whatever would change rates as it got farther and farther to the ground. All right, so let's compare the difference in these two tables. So if I find the difference in my H value and put it over my T value. So remember last week we were doing the difference in Y over X, the difference in Y over the difference in X. Well, the difference here would be minus 15 over 1. Okay, what about here? What is the difference between 270 and 255? Well, that's also minus 15 over positive 1. And we could try it one more time and we would see the difference in 255 and 240 is negative 15 over 1. Okay, so every time we checked any of these sets of coordinates, our slope never changed. It's always negative 15. Our slope is negative 15. However, let's look at the bowling ball scenario. What's the difference between 3 and 284? Well, that would be what? 16 minus 16 over 1. All right, what about 284 and 236? So 284, use my calculator, 284 minus 236 is a difference of 48 minus 48 over 1. And then let's look at the last two coordinates. What's the difference in 156 and 44? That would be 112. This is negative 112 over 1. So do you see that the slope between these coordinates wasn't constant? They kept changing. The numbers kept changing. So if you have a table that shows a constant rate of change, it's going to be linear. But if you have a table that shows slopes that change from coordinate to coordinate, it's nonlinear. Okay. All right, let me find my mouse. Go to the next slide, get rid of all this stuff. All right, so see if you guys can look at this table and figure out what the slope is between every set of coordinates. You guys do that, please. Send me the answer when you know it. What is our rate of change? If it is constant, what is it? Jaden, you're close. You got the numerator right, but not the denominator. Good, Penelope. That's exactly right. Anybody else? Good, Lynette. That's exactly right. All right, well, let's check it out. All right, how do we get from -2 to 3 on a number line? What's the difference between -2 and 3? If I'm on a number line and I'm sitting at -2, I want to get to +3. How many units would I move forward? 5, right? I would add 5. I'd go up 5. And here I would go up 2, right? So the rate of change from these two coordinates is 5/2. Let's see if it's consistent. How do you get from 3 to 8? You would move up how many spaces? 5 again. And then from 3 to 5, how many spaces would I move forward? 2 again. So this didn't change so far. And then 8 to 13, what's the change? +5. And then 5 to 7, what's the change? +2. So our change in y over change in x is 5/2, 5 halves. So the slope is 5 halves or 2.5. Okay. So if we graphed this table, we would get a linear function, which means what? What does that mean if it's linear? When we graph it, what would we see? Yep, we would see a straight line. That's exactly right. Good. All right, any questions on that when we're dealing with tables? No? Okay. All right, let me move forward. All right, let's look at this one, however. Of course, it tells us at the top that it's nonlinear, but let's just double check and see why it's nonlinear. So what would be our change from 2 to 11? On a number line, if we're sitting at 2, how many spaces forward would we have to go to get to +11? +9, right? So 9 over, what's our change? From 1 to 3, I would go forward. How many spaces? 2. So our rate of change between these two sets of coordinates is 9/2. All right, when we go to the next 2 points, if I want to see the difference between 33 and 11, 33 minus 11 is 22. So here there's a change of 22 over what? Yep, 2. So here I'm showing my change is 22/2 or 11/1, right? And then from 33 to 88, that would be +55/2. So our rates of change definitely are different, aren't they? So this is nonlinear, and that's why, because there is not a consistent rate of change. All right, everybody understand? You have any questions? All right, so I have 3 tables here. I want you guys to work for a minute. I'll be quiet, and I want you to figure out if these are linear or not. So we'll call this one over here letter A, letter B, and letter C. So when you send me your answer, please reference which graph you're talking about, please. Everybody send me answers, all of you, please. So far, all the answers I have are right. Good job, everybody. Keep them coming, please. Job. Good job, guys. All right, so letter A, our change in Y from 2 to 4 is +2. And then from -2 to -1 is +1. So 2 over 1. And then we see it here from 4 to 8 is +4, which is okay if these numbers change, but you got to make sure your final ratio or your final fraction doesn't change. However, this one is still +1. And then here we have +8 over +1. So this is non-linear because the slope kept changing. So A is nonlinear, okay? All right, letter B, remember it's change in Y. If I'm sitting in a number line at 12, how do I get back to 10? I subtract 2. And then from 3 to 6, I add 3. 10 to 8, I would subtract 2. 6 to 9, I would add 3. 8 to 6, I subtract 2. 9 to 12, I add 3. So I have a constant rate of change, a constant rate of change of -2 over 3. Good. And then letter C, from 6 to 8, I would add 2. From 1 to 2, I would add 1. And if you check the rest of this graph out, it's constant. 2 over 1, 2 over 1, 2 over 1. So this is linear, and our slope is +2. All right, very nice, guys. Those of you that tried it, you got I had almost every one of them right. Almost. Somebody just made one or two mistakes. That's all right. We're just practicing. All right, moving on. Okay, so just some general rules of linear functions. As long as your variables x and y are raised to the power of 1. So remember, if you don't see an exponent, it's a 1. So here, this equation is in slope-intercept form, right? This equation is in slope-intercept form. This one right here isn't right now in slope-intercept form, but it would be easy to solve for y and put it in slope-intercept form. And who can tell me what kind of graph this would be? Y equals 4. What kind of graph would that form? Remember Buck's Hoy? This would be a what kind of line? Horizontal line. Okay, but the point is that all of these all of these variables are raised to the power of 1. So if that's true, you've got a linear function. If you have an equation where all the exponents are 1 for all the variables in the equation, then it's linear. However, if any of these things happen right here, it's nonlinear. So y is to the power of 1, but if you put x under a radical, y equals the square root of 0, it's nonlinear automatically. Here, one of our exponents, I keep saying exponents, one of our variables has an exponent greater than 1, so this would not be nonlinear. Both of these variables have exponents greater than 1, so this is definitely non-variable. I mean, nonlinear. And then look at this one. If you have one, or the x is in the denominator, it's nonlinear automatically. So if you can remember these rules, you won't even have to graph anything to know that these equations represent non-linear equations, okay? And you guys have access to my notes because they're on today's Canvas page. All right, got it? And this is it basically over here. The x cannot be raised to a power higher than 1. X may not appear in the denominator of a fraction, and there should not be any additional symbols with the variable x. All right, so I'm going to ask you guys, like I did earlier, is it linear or nonlinear? Are you guys ready? Oh, but first we're going to listen to Mr. Buffington. It's 10 minutes, but I'm going to put him talking a little fast, so it won't be exactly 10 minutes, okay? Let me make sure I have shared the sound. Share sound. Nope. Oh, dang it. I stopped sharing. Sorry. Okay, here we go.
Hello, this is Mr. Buffington, and we are going to look at graphs of functions today. We're going to be looking at graphs of functions. So let's take a look here. The graph that you see up top with the green dots appearing and the other graphs are some examples of things that we will look at today. First off, there are a couple of differences between linear and nonlinear functions. Linear functions are equations that have x and y values raised to the power of 1, usually. Just x or y. There are some exceptions to this. Absolute value functions are not. They have x and y to the power of 1, but they're one exception. There's a couple of exceptions, but usually when you have x and y values just raised to the power of 1, they are usually linear functions, or functions that form straight lines. This is kind of the key here. If they can be written in standard form, which is some number times x plus some number times y is equal to another number, that is a linear equation or a linear function. They are often written in slope-intercept form, y equals mx plus b. This is the most useful form for linear functions. We get a lot of information from this. There's also something called a point slope form, but I think it's pretty dumb and I don't like using it. So anyway, there's a couple of different ways that you can write linear equations in different forms. And they look kind of like what you see there. Now, nonlinear equations have an x or y value, and it's usually, again, there are some equations that are different, but it's usually raised to the power of 2 or more. That forms, whenever x is raised to a power of 2 or more, it's going to form a non-linear function. And they may form waves or lines or all sorts of different funky things. But when they're raised to the power of 2 or more, they're going to form something other than a line. However, they will still be functions. Let's talk real quick about what a function is. A function is when you can draw a vertical line and it touches 1 or 0 points on a graph. So this one here where you only have 1 point or no points being touched, that is an example of a function. Over here where you see this line, this is a relation. A relation is just any set of ordered pairs. So basically if there is 2 points that are vertical of each other, okay, 2 points that a vertical line would pass through 2 or more points, then it is no longer a function. So you'll see that with a line, as long as it's not a straight vertical line, it would be a function because a vertical line would only touch it in one place. So let's look at the graph of linear functions. So I'm going to plot a couple points on here, put this line on. All right, this is an example of a linear function. Okay, the variables decrease or increase at a constant rate, which is called slope. And that's kind of the key factors of a linear function is you can draw it in a line, obviously linear is a line, and the rate of increase or decrease is constant, and that's called our slope. So linear functions have a slope and they look, in a nice straight line. Now, nonlinear functions get kind of fun. There's lots of different nonlinear functions. This one here, x to the power of 2, is if I were to draw these dots on here and form a parabolic curve or parabola. Okay, they have x raised to the power of 2. Now you could do x squared plus 5 or minus 5 or 2x squared minus 6, but the point is that you've got that x raised to the power of 2. You're going to form this kind of curve shape. Now adding numbers on the end or putting numbers in front or making it negative, that'll shift this graph up and down, side to side, flip it upside down so that it's opening downwards instead of upwards, make it narrow or wider, but you're still going to get that general curved shape. All right. So that's one very common example of a nonlinear function. Y is equal to x squared. A common example with word problems of this is comparing the side length of a square to the area of a square, because the area is equal to the side length squared. So that would be a common word problem type comparison of using this nonlinear function. And I'll show you an example of that in a second. First off, let's look at a couple more nonlinear functions. Y to the power, or y equals x to the power of 3. This one here is kind of funky. And again, the common example would be comparing the length of a side of a cube versus the volume of a cube. Volume is the side cubed, so you'd get kind of a funky little squiggly line. This is still a function because when you place a vertical line on it, it would only touch one place on the graph. One more that's not nearly as common and hopefully won't confuse you, and thank you to calculatorsoup.com for this picture that I stole, but when you're graphing a sine, okay, sine or cosine, tangent, when you start graphing trigonometric ratios, you get funky looking patterns. And this one is sine of x. Again, it's a trigonometric ratio of the side lengths of triangles. It doesn't really matter what it is. It's a wave, and when you put the vertical line in there, you would only ever touch one part of the wave at a time. So that's just a kind of another example of a nonlinear function. I just wanted to put one up there that's in a wave so that you can see what it looks like. It still is a function. It just looks kind of funky. Now, let's talk about, let's back up to Math 8, get out of trigonometry, go back to Math 8, and talk about a sample question, a sample Common Core type question that would relate to all that we've talked about. Juliet creates a function for some unknown reason. Juliet's bored. She creates a function that relates x to y. When she graphs the function, she finds that the relationship between x and y is non-linear, which would describe x and y. So we're going to need to know what linear and nonlinear look like. Remember the key, if it's linear, it has a constant rate of change, slope. All those other ones don't have a constant rate of change. So that's important to realize. So let's talk about these examples, again from the sample question I pulled. Y is the number of feet in x yards. No, this would increase at a regular rate because every yard is 3 feet, so it has a steady slope of 3. When our number of yards increases by 1, our number of feet increases by 3. It's a steady slope. Our next example, y is the number of cans of soda an X 12 packs. Again, this is not nonlinear. This is linear. It would increase at a regular rate. Each pack has 12 cans. Therefore, again, we've got a steady slope of 12. How about this one? Y is the area of a square with a side length of X inches. This is our nonlinear equation right here. As the side length increases, the area is squared. So I just put some points up there. The side length starts at 1, the area would be 1. The side length is 2, the area would be 4. The side length is 3, the area would be 9.
All right, so overall he made his point. It's got a little bit more to it, but that's the parts that I wanted you guys to hear. Okay. All right, so review time. Are you ready to review? All right, over here. Look at this one. Ireland, letter A. Is this linear or non-linear? Letter A, Ireland.
It's not.
It
linear.
is non-linear, Ireland. Yay, very good. All right, how about Penelope? Letter B, Penelope. Is this linear or non-linear?
It's linear.
It is linear. Very good. That is correct. Jaden. Letter C, Jaden. Is this linear or non-linear? Jaden's already typed linear. Very good. And who have I not called on today? Evan. Evan, letter D. Is letter D linear or non-linear? Yes, Evan messaged me. He said non-linear. All right, I think you guys got it. Good job. All right. How about this one? Letter E. Aiden. Letter E. Is this linear or non-linear? Aiden said this is linear. I agree. That's exactly right. All right, what about letter F? This is a tricky one. What do you think, Angel? Linear or non-linear? It's a little tricky, Angel. Go with your gut, Angel. What do you think?
Non-linear.
It is non-linear. So even though this part of the line, these are definitely both straight lines, right? However, since the slope goes from negative to positive, it's not a constant rate of change. So you're exactly right, Angel. Good job, good job. All right, letter G, Alex. What is this, Alex? Linear or non-linear, Alex? What do you think? He's thinking. Oh, he said linear. Very good. Yay. And one more. Kumar, letter H. Kumar, is this linear or non-linear? Letter H. Kumar is thinking. Kylie actually beat you to it, Kumar. She said non-linear. Yay, that is correct. Y'all are learning so much. All right, these are the ones that require a little bit more work, right? Yeah, Kylie, you beat Kumar answering that one. All right, everybody look at the first one. What is your first impulse? Linear, non-linear? Yep. The majority says non-linear. You're exactly right. Good job, guys. Because if you just look from here to here, this is +3, +1, but this is +6, right? So 6/1, 3/1, definitely non-linear. This one's non-linear. All right, look at the second one real quick. This one right here. These are easy because the input for all of these increases by 1 + 1 + 1. So really it's all it is up to the Y values. Right here, guys. Linear, non-linear. What do you think? I got 2 good answers so far. This one right here. Can y'all see the one I'm circling with my little mouse? Oh, you can't see that? Oh, I'm sorry. Let me choose. Sorry, I thought y'all could see my mouse. This one. Is it linear, non-linear? What is it? Good. Yes, yes, yes. Oh, y'all knew. Y'all just didn't know what I was talking about. Yeah, it's linear, right? Plus 2 over 1, plus 2 over 1. Good job, good job. All right, what about this one, everybody? Good, y'all are doing these very quickly. 3 over 1, 3 over 1. So linear for sure. What about this one? Yep, this would be plus 3 over 1, but this would be 5 over 1. So this is non-linear. Good. All right, now we're going to check our equations. Remember the rules for the equations? What about this one? Let's look at the first one over here, the top left. Linear, non-linear, which? Why is this not, you're right, guys. Why is this non-linear? What makes this equation non-linear? I got one good answer, only one. Y'all don't know, you're just guessing, or do you know for sure this is non-linear? Remember, guys, it's all about the exponents. If you have an exponent greater than 1, it's nonlinear. That exponent of 2 makes this nonlinear. That was one of the rules. Your exponents can only be a 1. All right, what about this one right here? Linear or nonlinear? And like I said, if you haven't memorized these rules, which you probably haven't, this slideshow is on Canvas for you. No, this one's actually non-linear because one of the rules said that you cannot have a symbol basically connected to x. So this is 3 square roots of x. You're not allowed to have square roots. Yep, no extra symbols. You're exactly right. All right, what about this one right here? Linear or non-linear? Yep, it's non-linear. Who can tell me why this one's non-linear? Yep, one of the rules is the x cannot be in the denominator. That's one of the rules. The x cannot be in the y. Technically, the y could be in the denominator, but we're not going to try to trick you like that. If you ever have an x in the denominator, it's nonlinear. All right, what about the last one? Linear or nonlinear? This one is linear. In fact, this is written in slope-intercept form. Y equals mx plus b. So this is definitely linear. It's in our slope-intercept form. Okay. All right, guys, guess what? That's it. But just to remind you real quick, the rules that we were just talking about are on this slide, right? I passed it. Where's the rules? Here they are. These are your rules for non-linear functions. Your x cannot be around a symbol, connected to a symbol. You can't have an exponent greater than 1, and x cannot be in the denominator. Okay. All right, so basically, guys, what's happening now is, let me look what's going on tomorrow. I think you have a Delta Math assignment for Friday. Yes, so for the 11th, and some of you have already done it, of course. You guys had 2 mixed reviews this week. Not very many people have done those, so make sure you get all your math done this week. So you had 2 mixed reviews, and tomorrow you have a Delta Math, including nonlinear and linear. Monday, all I have is like some review games for you guys just to practice everything we've learned this unit. Tuesday, the only reason we're we are meeting. Oh yeah, I do need to tell you one more thing before your test. So next Tuesday, you'll be working on your study guide, but I also have to show you one more thing. On Wednesday of next week, you'll watch my video to check your study guide answers. And then next Thursday, a week from today, when we meet, you guys are going to take your test over this unit. Okay? Everybody know what's going on? All right. Thank you guys. A lot of people were absent today, but you guys weren't. You guys rock. I appreciate that. I'll see you guys tomorrow for advisement. Everyone have a great evening. Thank you. Bye. Have a good day. Bye.